another event happening on campus at 9. So I started the recording and I'll be back as soon as I get the other thing started. Make sure
Okay.
it's okay. All right, but you should be all set.
Okay, great, thank you. So the sound is working?
Yeah, the video is on.
Can I just double check? Let's see if I can figure that out. Oh, yeah, so can you hear me? I guess that's you, Sam.
Yeah.
Can you hear me now? All right, great. Good morning.
Hello.
Good morning.
I was completely out yesterday because of the vaccine.
Oh, yes.
Phew, this was devastating.
Yeah, but now you're fine, huh?
99.
So what, you had a fever or?
I didn't have active fever, but I had very hot, very cold, shivering, body ache,
My gosh.
dizzy. So I didn't do anything. I couldn't even watch TV. Nothing.
Wow, that bad.
Yeah.
Oh,
But it was not bad in the sense that I knew, okay, tomorrow it will be over.
yeah. I should probably, so what is the rule now? If you're over 60 or something, you can get
65 is the cutoff.
60.
I passed the cutoff.
But they don't really check, right? Or,
You sign that you're over 65.
oh, yeah, okay.
But if you have underlying conditions or something,
Yeah, yeah.
I don't think you will be prosecuted if you. I think people who are not vaccinated should be prosecuted.
But, you know, my second vaccine was in May, so I
Oh, so you still
supposed to wait 6 months or something, right? The
yes,
booster.
so you don't even have 6 months now.
No.
So that's another reason. But that also means that you don't really need it now
Yeah.
because it decays after 6 months.
Actually, I should say we're live, although there's nobody online.
Oh, you're alive. My view of these things is that we're alive anyway, whether we know about the microphone or not.
That's true these days.
The NSA or somebody probably listens. So I saw you switch your time at the conference.
Yes.
It was related. This was part of the reorganization that I was.
Yeah. Yeah, I was looking for a Stony Brook talk, but I can't find it anywhere online. I guess it's the Simon's.
It's the Simon's collaboration.
Yeah, but it's not publicly announced the link anywhere. It wasn't on the Stony Brook
It
website.
actually, mine overlaps with your class, which I tried to move. I guess the class cannot be moved, so I tried to move my talk, but that couldn't be done. So I'll be on a panel with Dan Fried, with the title, What is Quantum Field Theory?
This is where?
This is kickoff conference for this new Simon's
Oh, I
collaboration.
thought that already happened this week. Oh, it's next week.
It's the week after next.
Oh, okay. I thought it was this week.
No, it's the week after next.
Maybe that's why I couldn't find it.
There's so many things.
I was looking for it yesterday. Oh, now he's giving a talk. Let's find it. I couldn't find it. Yeah, there was a talk yesterday by John McGreevy on fractons.
Yeah, I heard that talk already.
Yes, I think I heard very shaped it. But the introduction was okay. Nice.
That was
I asked my usual question. You may have noticed if you were there.
the robustness of this.
Yeah. I just want, I know it's, but I just wanted to know at what point you would make some general statements. I want to know exactly at what point.
Yeah.
This was your
No,
question.
this is an absolutely crucial question. And you know that high energy physicists and condensed matter physicists have a different view of this, which I summarized in one of my papers.
Yeah.
So we call it naturalness,
Okay.
which means that we declare a symmetry and then we write all the terms that are invariant under the symmetries.
Right.
You have a stricter condition.
Yeah.
That you also want to write terms that violate the symmetry and make sure that they're not relevant.
Yes. Yeah. Yeah.
This is really a stricter condition than
Right. Right.
and both are valid as long as we know which one we're talking about.
Yeah.
Michael Levin, I think, will give a related talk here in the UQM meeting.
You mean in New York, or
Here.
he will give you?
Yes.
Oh, okay.
So Michael Levin was a co-author on the same paper with McGreevy and Chen.
Oh, I see.
Now a
Yeah.
new postdoc.
Right. Right.
He will give a talk here on
Is the UK meeting with this room or in Wolfenson? Or?
we booked the 2 rooms.
Okay.
So we booked the 2 rooms depending on how many people there are.
Oh.
And we also rented a tent.
Yeah, I had that email from Mike. Yes.
Oh, that's right.
Oh, that's cool.
I am so impressed with Mike's organizational skills.
Yes. I know.
You know, every time there's an email to everybody with the 3 of us signed,
Yeah.
that meant that he wrote it. And I said, yeah, that's okay. And Ashwin said, oh, why won't you just add another word here? That's the level of it.
Right. Yeah, it's great that we found this talent in it.
It's also great if we don't have to travel.
Yes. I think.
Well, some people are coming. Some people really be careful. Can we talk later today? What's your schedule? I have a meeting at 11. 11:30. Right after lunch. Or no,
It is a group.
it's a group. Let's talk right after lunch.
Fix it here. Hello, Kabir, are you there in Hyderabad? Can you hear me? I hope the sound is on.
Yeah, we can hear you perfectly. Thanks.
Okay. All right, great. Okay, it's about time then. Wait till 9:02. Anyway, okay, so good morning and good evening in India. So let's get started. I hope you can all hear me. So what we're doing today is, will hopefully complete, is the Paramagnon theory of metals. And then after that, we're going to start more modern topics on spin liquids and so on. But let's continue the discussion of the Paramagnon theory. So we're looking at the Hubbard model, which I've now written in a slightly different way. There's some dispersion epsilon k and some interaction u. So this is a model of fermions. And what we're trying to do is to come up with some understanding, not just of the fermionic excitations, but of bosonic excitation. There are another set of sometimes called collective modes or bosonic modes that can be present even in any system of interacting fermions. And in this case, we are going to look at the collective mode associated with spin fluctuations. Now this kind of...
Hello, sir. Is there any reason of writing Hubbard model in particle hole symmetric form?
Well, it's not necessarily particle hole symmetric because I've absorbed the chemical potential in the definition of epsilon k. Okay. So this term is particle hole symmetric, but this is not. So this is just a choice. And yeah, so you make a choice in the way you've written it. And I made this particular choice because for this particular choice, this second line here is exact. If you integrate over the phi, you get back exactly this term, which is particle hole symmetric. And so is this, the spin, has a particle hole symmetric form. But that's a choice you make. And that ties in with the point I was starting to make. If you start out with any system of interacting fermions, you make a certain choice in the structure of the interaction term, you can rewrite it as a theory of fermions coupled to some boson in many different ways. So this is one way to do it, couple it to the spin density. If you made a choice of coupling it to the charge density, then you will get a theory of plasmons or zero sound modes in this liquid. If you made a choice of coupling it to the Cooper pair term, which is what we did last time, and then you'll get the Landau-Ginzburg theory of superconducting order parameter and its fluctuations, which include the plasmons, the Higgs fields, and things like that. Yeah. Or if you have short range interaction, they include sound modes. So really, many things in condensed matter physics are of this flavor. They're presumed to be okay for moderate interactions, and they're not controlled by any expansion parameters. There's just some physical insight in this particular system. For example, the electron Hubbard model. We want to focus on the spin density fluctuations. Here, the insight comes from the fact that at large U, we know the system is an antiferromagnet. So let's assume that's a correct conclusion, and then try to apply that for smaller U. That's the strategy. I mean, even in particle physics, this strategy is used when you start from QCD, the theory of fermions coupled to gauge fields, which give you some long-range interactions. And then you rewrite it as a theory of pions in the chiral Lagrangian. That's pretty much the same thing. They use different tricks to figure out the structure of the chiral Lagrangian, but it's in exactly the same philosophy here. You're rewriting a theory of fermions with interaction to theory of fermions coupled to some bosons. And the choice you make for the boson is really some kind of guesswork as to what is the important boson in any given system.
It's usually one boson at a time, right? So we
Yes.
have these excitations or we have the charge excitation.
Right, exactly. So, and that's so one pointing out an important point is you have to make a choice. So we make a choice that you're going to focus on the spin sector, but maybe the system really ultimately becomes a superconductor. So that's kind of the direction we're going to go today. We're going to see that, even though you make this choice, if you now look at higher order corrections in this channel, you can see the effect on some other boson. But a fully self-consistent theory with all possible bosons is a very difficult thing, and there's no general way to do that. Yeah.
Correct me if I'm wrong, but one important difference between this and QCD. Here, I think what you have in mind is that this Hamiltonian is a representative of a large family of Hamiltonians.
Sure.
And as you vary the parameters in this large space, you might land on the region where one description or another is more appropriate.
Yes.
This is unlike QCD, where we do not have the other parameters.
Yeah.
There's only one QCD, and the goal is to find the answer.
Okay, well, there's only one lanthanum copper oxide, and I mean, we have a similar issue here. So here, and there's different arrows I drew on the phase diagram last time were different choices. So here we're making the choice, I guess motivated by experiments and large UX analysis, that we focus on the antiferromagnetic channel first. And then we look at higher order corrections in this channel and find results corresponding to the pairing channel, which we did yesterday or last time, when we decoupled this term in the PCS channel, in the Cooper pair channel, and we found D-wave superconductivity. What I want to show you today, that even in this other channel with spin fluctuations, you will end up with the same answer. Yeah.
I think you said it last time, but is there a reason why we can expand in small phi, or we're just considering configuration where the bosonic excitations are small in amplitude?
Yeah, it's the second statement. There is no fundamental reason that we can truncate this. I think the one place you can argue in general grounds that you could is at finite temperature. So you start at high temperature where where there's no broken symmetry, and then you're approaching the critical point where this first turns negative. So when this is small, this quantity is small, then you can use the logic of Landau-Ginzburg-Wilson and approximate this.
So we are assuming that if we excite a small bosonic fluctuation, it doesn't build up to big amplitude range, or it could.
Yeah, I mean, and that argument is the same as the argument that Landau originally gave. Right near the phase transition, there is a small parameter, which is this number. And provided this number is about a 1, while this is small, then you can control it.
Thanks.
Okay, I should say this Paramagnon theory actually has its origins in helium-3, where there is a very similar sort of issue. The difference between the electron Hubbard model here and helium-3, there are two differences. One is you're in 3 dimensions, not 2. And the other is that you don't have a lattice, so just have a continuum dispersion. You do have some very short-range interaction in helium-3. And in those conditions, it turns out the natural spin fluctuations, we believe, are ferromagnetic. So the original theory of Paramagnon for ferromagnetism in helium-3, and there it leads to P wave pairing, not D wave pairing. And all of that, you know, what we're doing here is kind of an image of what was done earlier in the 60s and 70s for helium-3. Okay. All right, so these statements as written are formally exact. This is just an exact representation of the original model in terms of path integral over fermions and bosons. This is a boson, which is a vector in spin space. And then I can just do the path integral over C, order by order and phi, because, you know, this is the only term that involves any nonlinearity now. It's kind of a Yukawa coupling between the boson and the fermions. And so to second order and phi, you get a correction to this quadratic term. This term is the same as this term. And you get one correction from the second order graph in phi. And that gives you this famous Lindhardt correction, which it's negative in sign. And that's good because this is telling you that the effect of the fermions is to make phi fluctuations stronger. So when this coupling goes to 0, then phi becomes very important. If it come with the opposite sign, then that would be a signal that you're looking at the wrong boson, because it's getting even more expensive to create it. Okay, so that's kind of where we were. Any questions in India? Okay, so so we're going to look at 2 possible fates of this theory, which are connected. One is that we go not to superconductor, but to an antiferromagnetic metal. So let's look at a theory of that. So there, the idea is that all of these terms here, you compute them, you figure them out, and you find that this path integral over phi is dominated by some non-zero saddle point. So we assume that phi, which in general is a function of momentum and frequency, we're going to replace it by its expectation value. Let me write it in space n. Okay, so tau, let's call it R, is going to be some autoparameter, which I guess I forget what I called it last time. Let's call it phi 0 today, times some spatial modulation, cosine of, okay, not changing notation from last time, but there's certainly a consistent notation in the notes. And this, let's make this a vector. Okay. And K, we're going to take to be pi pi. So this is, you know, exactly what the condensate is and what wave vector it has is, you know, depend on all kinds of details. And in the real world, you'd require a better calculation that we're doing here than just computing the Lindhardt susceptibility. You may have to do the full theory and understand this better. And there are sophisticated methods of doing such things numerically. But let's just use our insight from the large U limit, where at least at half filling. So imagine we're exactly at half filling. At large U, we know an antiferromagnetic pi pi. Now we stay at half filling and we move and we reduce the value of U. So under those circumstances, this is a pretty reasonable assumption. So that's the simplest case that we're going to look at. So now once we have a non-zero expectation value, we want to go back to the original Hamiltonian and rewrite it. So the electron Hamiltonian now, so this is the state in a, so what we're looking at is an antiferromagnetic metal. That's what we're going to present a theory for now. And the Hamiltonian for the antiferromagnetic metal for the fermions is going to be somewhat K, epsilon K, C dagger K alpha, C K alpha. Okay, that's the free fermion part. But let me actually even play a little trick there. What I notice is that this term, if I take this space dependence and plug it in here, then what that term is going to do is scatter an electron from momentum little k to momentum little k plus capital K. So it's going to mix little k with k plus capital K. And that's it, it's going to just mix those two because 2k is just 0 for this special value of k. So I'm going to say, well, let's just pick a set of values of k, and I'll put a prime here. And then I'll put the other ones, C k plus k. Okay, so what is this prime about? Well, this prime is a question of the Brillouin zone. So this is the original Brillouin zone of the full square lattice from minus pi to pi. So I want to pick a choice of k so that little k and little k plus capital K extend over the full Brillouin zone. And one convenient choice is to take the diamond. So if I take this diamond here, so this is where the sum 1 k prime is in this diamond. And so k is sitting inside, k is some point here. And now if you choose this diamond, then you can see that, so for example, if I add pi to this k, I'll go somewhere there. At that point, okay, I'm probably not going to do this right. You go somewhere here, but then you subtract 2 pi and you'll come back somewhere here. So this will be k plus k. So the claim is that if I extend over small k in this diamond, this is called the reduced Brillouin zone or the magnetic Brillouin zone. This is all I have to do, and these points will all be in these regions. So this would be the second Brillouin zone. All right, so all I've done is just rearrange the original term over there and read it in this way. You can always do this if you wanted to. It'd be silly to do this for a problem that didn't have capital K as a special wave vector, where it's the exact statement. All right, so now, however, life becomes simple because this term also can be written in the same form. It's very natural in the same form. And in fact, I put a big square bracket here because I'm going to get mixing between the same two terms. Yeah, so what will I get? So let me just put this in the z direction. Take this with the z hat here. So then I'll get, and I've called this in my notes, so let's be consistent. Let's call it delta 0. Delta. So it'll play the role very similar to the staring gap, but in this case, it's a spin density wave gap. So we'll get minus delta and C dagger and sigma z z theta, which is of course diagonal, and you'll get C dagger K alpha C K plus K theta summation conjugate, and That's it. Okay, so this is, the exact analog of the BCS Hamiltonian, where you had some 3 electron dispersion. Now, in the BCS Hamiltonian, they mix together spin up, K with spin up with minus K with spin down. Here are mixing together K with spin up with K plus K with spin up. And spin up and spin down kind of decouple, because this matrix is diagonal. And so you just have two 2x2 matrices to diagonalize. So this can be also written as K prime, something like this, C diagonal K alpha. Okay. Okay, so if you don't have any fancy Bogoliubov rotation to do, it's just a matter of diagonalizing a 2x2 matrix. And so we can go ahead and diagonalize this and get our final answer. So this is going to be equal to sum on K, some dispersion EK. What did I call it in the notes? So here there's no natural spin symmetry. I call it EK plus minus. Plus minus, this is not spin. There's one also for spin alpha, but it does depend on alpha. Let me just call it D, dagger plus minus alpha, K, and D plus minus alpha. So this E plus minus are just the eigenvalues of this 2x2 matrix. So what are those? EK plus minus is, of course, EK plus K over 2 plus or minus. Real, okay. Yeah, okay, so that's the usual, just a very simple matrix to diagonalize.
Sorry, is the K sum on the right still primed or?
Yes, it is, thank you. Okay, yes, question there?
Yeah, sorry. So there was some confusion about how did you get this HAFM from the Lagrangian using the phi?
Oh, sorry, I erased that. So there was a term here, which is still visible slightly. C dagger I alpha sigma alpha beta. Oh, there's a factor 2 that I've lost somewhere. C I beta. So there was a term like this.
Yes.
And I just inserted the top line in here for phi. And just evaluated this in momentum space. Okay, so this gives you e to the I k dot r as delta. And if you take a Fourier transform here, you'll get C dagger of little k e to the minus I k dot r, and you'll get C k dq of e to the I q dot r. And you do the sum over r, you will get the condition that q equals k plus or minus k, something like that. And that's what I did. All right.
I see. Thank you.
I'm sorry, this should be capital K. Okay, so it just came from this term that was in the original theory. Okay. All right, so this part is simpler than the usual BCS theory. The more complicated part is just figuring out what this means. So now these are just ordinary fermions in the grand canonical ensemble. And what we have to do is figure out, so we occupy all fermion states.
Sorry, why is it important to limit the grand canonical rather than? We can work with fixed numbers, but you did not mix creation and annihilation.
True, but there is a chemical potential inside epsilon K. And it could be, in fact, in general, when you add these extra terms, that you would change the total density. So we're working at fixed mu. Maybe that's the most important part. Fixing mu and we're letting the density be whatever it wants to be. Okay, so to find, what the density is going to be, we're going to occupy all the negative energy states. That's the usual thing, finite density fermions, and that's going to give you a Fermi surface. So that's really what we want to figure out. What is the Fermi surface where you have zero energy fermionic excitations? And how is it compatible with the Luttinger theorem? All right, so this is where the tricky part comes. I mean, formally it's not very complicated. You can just put this on Mathematica. You can put this function, which is a rather complicated looking function on Mathematica, and then just find all states that occupy this, and then you'll be done. But let me try to do it by drawing some pictures. And this is a little tricky, but so I'll try to be okay. So we'll take the full Paramagnon zone. And first, let's look at the points which were occupied when you didn't have any of this fancy stuff, where you just had some dispersion epsilon K. So in the cuprates, so let me just take the example of the cuprates. So I'll pick a color for that. This is the underlying Fermi surface. Looks something like this. And this is, let's imagine we're half-filling. And so this is the region here where epsilon K is less than 0. These are the occupied states. So these states are all occupied. And this line here is epsilon K equal to 0. That's the Fermi surface. And and you can see pictures of these things in many, many experiments. You can literally map this out to high precision. Not exactly half-filling, but anyway. Okay, so the other quantity here is this one, Ek plus K equals 0. So let me draw that in green. So that's this thing shifted by pi in some direction. Okay, so if you shift it, basically you're taking this object, this center here, and moving it over there. And then you'll see that this orange Fermi surface, this becomes a big circle. So then I can shift it back to the original Paramagnon zone. And so that equation will give you this curve, something like this. Forgive my poor ability. So this is the line, Ek plus K equal to 0. And what are the occupied states now? Well, the occupied states are here. Okay, so those are the occupied states. Okay. So you'll see something interesting in this picture already. If you look at the orange and blue, orange and green shaded regions, there's the majority of the regions have only either orange shading or green shading. But there's two regions where it's different. So there are these regions here, which have both orange and green shading. And there are these regions here where you have neither, they're empty. Okay. All right. I mean, just keep in mind, all I'm doing is solving this problem. That's all. You just try to do it in pictures. And if you have any doubt, just put it in Mathematica, put some dispersion, and let it do it for you. All right, now we have to turn on the delta. And similarly, we're going to ask what is locus of points where this vanishes. Okay, well, so that's also relatively easy to construct. Basically, what's going to happen for sure is, so you have to look at these points here where they intersect, where both are 0. So these are the points, sometimes called the hot spots. Terrible name, but anyway, that's what people call them. So the hot spots, both of these are 0. And then life is simple, you know the eigenvalues, the plus or minus delta. So what's guaranteed to happen at the hot spots is you open up a gap. That's where you have a gap. There are no gapless fermion excitations there. So they're kind of like double repulsion, you're going to open up a gap. So then now you can just figure out what's the locus of points where this is 0, and they'll end up looking something like this. Another here, like this. Okay, so now we have solved graphically the equation. The purple, this line here, these pink lines are EK plus minus 0. Now these are the actual fermionic excitations. And so these are the Fermi surfaces. So the Fermi surface now has split apart into many disconnected pieces. There's 4 pieces here along the diagonals, and there's 2 pieces on the so-called antinodal points. This is the same as that if you move this over by 2 pi, you get a circle here. And similarly, move that over by 2 pi, you get a circle. So there's 2 pieces here, and there's 4 ones in here. However, you have to remember the prime. So you have to divide everything by half. You only want to take the ones inside the diamond per one. So, but I won't. That's a factor of 1/2 that you have to keep track of if you're actually doing some calculations. Yeah. Is that a question? All right. So the other thing you notice, if you look at these Fermi surfaces, that they're. So what does this Fermi surface separate? So what it separates is an empty space with one band occupied, one band here and one band occupied. This separates a doubly occupied state with one band occupied. So these are sometimes called whole Fermi surfaces. And these are electron Fermi surfaces. So if you look at the quasi-particle, it has positive charge as you go from inside to the outside. Here, the quasi-particle has negative charge as you go from inside to the outside. This, of course, has very important consequences for photo emission. So you will see very different pictures away from zero energy when you look at these Fermi surfaces. Okay. And what about the Luttinger theorem?
Can you repeat, I mean, why you are calling that whole Fermi surface and why it is electronic Fermi surface?
Yeah, so look at the orange and green shading that hopefully that's visible to you. So the orange shading tells you when, when the original parent band is occupied with EK, dispersion EK. The green shading tells you when EK plus K is occupied. So if you look at the whole pocket, I mean, don't look at the, imagine that the pink line is just very, very close to these green and orange lines. That's, delta is very small. Then what you see that this region here, this empty region, is abutting singly occupied bands, either the green or the orange. So you're going from an empty state to a singly occupied state. That's what a whole pocket looks like. Here where you're increasing the occupation number. Here, when you go from inside to the outside, you have two states occupied inside and one state occupied outside. So you're decreasing the occupation number. That's the usual thing for an electron Fermi. In an electron Fermi surface, there are more, a state is occupied inside and it disappears when you go outside. But in this region, there's nothing occupied inside, but it appears outside. So so it's a positively charged quasi-particle. Okay, now if you're exactly at half filling, then the area enclosed by the hole pockets must equal the area enclosed by the electron pockets. So the number of holes must equal the number of electrons, because in the double unit cell, you have 2 electrons per unit cell. So remember the Luttinger theorem, I haven't fully derived yet, is modulo 2. A filled band here corresponds to 1 electron per site of the square lattice, because in the double Brillouin zone, there's 2 electrons per site. So effectively, the half-filled system with 1 electron per site has a net density of 0 electrons, mod 2, per unit cell. And therefore, at half filling, the area of the electron pockets must equal the area of the hole pockets. So now we can understand what could happen as a function of u. So let's try to draw at least at u equals 0. What is the phase diagram that we are getting here? Sorry, we're getting into some rather messy solid state physics here. But all of this has been measured in great detail, so it's important to understand it. So my usual phase diagram I had of the Hubbard model. Let's just focus on the half-fill site. So this is the insulator with up-down. This is, oh, sorry, no, that was interaction, T over U, this is V over U. So let's say we're exactly at half filling. So on this line, N up, Ni up, plus Ni down, equals 1. So in our universe, we have some, imagine it's this mean field theory, there's some region here, very large U, where phi equals 0. So you have a state that the Fermi surface looks like this. And these are the occupied states. And this is phi equals 0. So there's some, a very large U, there's some region of that type. That's, I think that's a reasonable assumption. And since I'm exactly half filled, the area of this, the area of the occupied states is exactly 1/2 times the area of the Brillouin zone, which is 1/2 times the Brillouin zone area, the full Brillouin zone area. Okay. So that's consistent with Luttinger theorem, because at this point I have not broken any symmetry. I have 1 electron per unit cell. And so the area enclosed by this should be 1 in appropriate units. 1/2 because of the fact of spin. So they spin up and spin down, both completely occupied here. All right, so now I increase the value of u. So what we imagine is that as a function of u, if this is phi, as a function of u, so it's 0 for a while, and there's some critical value uc where it starts to go up. So what happens? Well, what you get an intermediate region here, where you get the picture I just showed you. So you have the hole pockets. And you have the electron pockets. Let me double shade these, the doubly occupied. Those are the empty states. And the area of these electron pockets should equal the area of the whole pockets, despite my poor drawing, exactly at half filling. And what does phi determine? Well, phi determines, I can just, which is delta, sorry. You can just see from here, 2 delta is the gap at the hot spot. The hot spot is the point where both of these vanish, which is right here. So there's a gap at this point, which is the hot spot. There's a gap between the lowest unoccupied band and the highest occupied band, which is 2 delta. That's a mass gap at those points. But there isn't a mass gap at other points in the Brillouin zone. That's the difference from particle physics. In particle physics, once you get a mass gap, you're done. If you're not done, you could find zero energy fermionic excitation somewhere else. Okay, so this is still a metal, and it's the object we're studying. This is the antiferromagnetic metal. Yes.
Just as a general question, to get quantitative agreement, do you need to include higher order terms than phi?
Oh, you mean to quantitative agreement, the value of phi?
Well, there is no small parameter suppressing.
Yeah, I mean, I think to get quantitative agreement, if you fit the value of phi to the observation. So you know epsilon k from here, then you just have one free parameter, which is the value of phi. And you fit that to the position of these pockets, and then that works. Yeah.
But you're basically doing semi-classical expansion that would be justified by large n, for example, like.
I haven't justified by large n. There could be a large n to justify it, but I haven't. You could introduce some extra indices to justify this particular channel. Yeah.
But quantitatively it matches experiment. Well.
Yes, well, I don't think anybody can actually compute the value of phi from first principles. That's much harder. But if you allow phi to be a free parameter to match the experiments, and also epsilon k, which you map another set of experiments, then it will work.
So you have to measure epsilon of
You measure epsilon of k here or somewhere else, or at higher temperatures, where phi is 0. So then you find this curve that gives you epsilon k. You fit that to some reasonable functional form. And then you turn on a phi and you get this dispersion, and in many materials that'll work pretty well. But you have to fit the value of phi, and it's not much of a fit. You just measure the gap at this point and it gives you the value of phi. So, and then you just use that. So you use the gap that you measure here, the dispersion you measure here, and then you can predict where the Fermi surfaces are.
But then all that goes is this formula, right? Nothing else.
That's it. That's it. Yeah. Yeah. It's all about changes of bases, right? Like the CKM matrix. It's not so different. Okay. All right. So then what happens? Well, as I keep increasing phi, so here I'll have a metal, the ordinary metal. Then I have a region here where it's an AF metal. Then you'll find a point where it becomes an AF insulator. This is mean field theory, where the Fermi surfaces disappear. You keep increasing the value of phi, and these keep shrinking, and these keep shrinking. And since the areas have to be equal, they can only shrink at the same point. So there's some point where they disappear, and then you're in this phase. That's an insulator. Of course, in this way of doing things, the gap is very small. I mean, it could become larger at this point, but the gap you would estimate from this approach, which is in some sense your small parameter in the whole theory, is very different from the gap you'd estimate here. At u equals infinity, the gap would be an excitation where you take the fermion from here and move it there. That costs an energy u, practically infinite. Whereas here, this is a small u theory, the gap is small, but you're getting the same state, at least in the sense of all its basic characteristics. This state is an insulator, it's got a gap to all fermionic excitations, it has a broken symmetry, and all of those features are present even over here. Okay, now of course this is mean field theory, and surely at this metal insulator transition, you have to do much better to do a full theory of it. Yeah, I mean, I think there are people who study that, but we won't go into that. Yes.
At the metal insulator transition, the SU2 spin symmetry is being restored. If I
No, it's not. It's an antiferromagnet. This is a AF.
Oh,
I mean, this is the scenario I'm exploring.
I thought the antiferromagnet actually, you drew a classical picture, but I thought it actually is like a nonlinear. Oh.
That's at finite
Two
temperature.
space dimensions.
Yes.
In one space dimension, it would have.
Right.
Space dimensions.
Yeah, we're in two space. So we have zero temperature in two space, and the symmetry is broken. I mean, you could imagine other models. Yeah. And so there's a lot of work on such exactly the scenario you discussed. But you have a transversal insulator transition where at the same time the spin rotation symmetry is restored. And that has to be a much more involved theory because you have two different things happening at the same point. And that's kind of the logic between these deconfined critical points that some of us have spent a lot of time on. And so there are more exotic critical points involving fractionalization where something like that can happen. We're probably not going to talk about that now for sure, maybe sometimes towards the end of the course. And in fact, that scenario that will go from, well, in fact, the more attractive scenario is the other way around, where you go from an ordinary metal to an antiferromagnetic insulator with a broken symmetry. That seems to fit certain data and heavy fermion compounds, but this kind of mean field theory will not give you that. So here the broken symmetry is playing no role once you cross this point. So the broken symmetry is broken and we can forget about it. Now we're just following the Fermi surfaces. Yeah.
I'm a little bit confused about this point because the model is gapless everywhere, right? Because you have the Goldstone bosons of the broken.
Okay, great point. Okay. So this theory has two classes, this theory here, the antiferromagnetic metal has two classes of gapless excitations. There's the fermionic excitations with charge plus and minus E, which are on the hole pockets and the electron pockets. But there's also a bosonic excitation of spin 1 with charge 0, which we haven't discussed. But to discuss that, I have to go back to the theory for phi and look at phi fluctuations. So those are the spin wave fluctuations about this state. And they are also present here. That involves a much more difficult calculation.
When you say gap, you meant the gap in the electronic excitators, not the gap in the bosonic excitators. The full system is still gapless.
Correct, correct. Yeah, so this system has a gapless bosonic excitation, which is the spin wave excitation. We figured out the spin wave excitation here in the insulator using the Holstein-Primakov method 2 lectures ago. That same excitation is still present here. That's a bit more complicated to figure out, but I've given you all the tools to do it. You have to go back fermionic path integral, integrate out the fermions in the presence of a broken symmetry and look at the effective actions for the bosons there. And that would be the exact analog of the Cairo-Lagrangian calculation. But done, we integrated on not massless quarks, but fermions that have this a much more complicated dispersion relation.
What is known about the transition point?
I'm just sorry. This is a relatively simple transition point, I think, because you can the density of active fermions is very small, so you can do a low density expansion, and so there aren't any singular corrections. There's some log corrections that come in, but not much more. So the free theory for this particular transition, I don't know if this even been seen in any compound. It's relatively simple. Where the broken symmetry just is present on both sides. So you can do kind of a low density expansion at that point.
Hello, sir.
Yes, go on.
You once talked about incommensurate to commensurate transition. So what would be different in case of an incommensurate wave vector?
Yes, so So the nice thing about this particular wave vector phi was that I only need a 2x2 matrix. But if you, in general, if you took some k like this, let me call it p, 2 pi p over q. And let's take a commensurate wave vector 2 pi p prime over q, where these are co-prime numbers. If I took this particular commensurate wave vector, you get a q by q matrix that you have to diagonalize. And in typical, you may end up getting q different pieces of your Fermi surface. So if you have q going to infinity, which is the incommensurate case, you'd have a dense set of Fermi surfaces. It becomes a very complicated problem. But luckily, even for the incommensurate case, the approximation, we just keep a small 2x2 piece in the vicinity of any wave vector is pretty good. And the spectral density on that dense set of Fermi surfaces becomes extremely small. But yes, in principle, the incommensurate case is a much more complicated version of the same calculation. I mean, you do the same exact calculation, except you diagonalize bigger matrices. Okay.
Are there cases where it can be viewed as a disorder, like an electron moving?
Well, those are slightly different, I think, yeah, but that's an interesting question. To what extent does a quasi-crystal, which is also incommensurate, look like a disordered crystal? Mathematically, they're very different if you're really looking at the nature of the spectrum. But in practice, there's always a few impurities, and so they end up looking quite similar. Okay, so that's at least one set of calculations where you can match the strong and weak coupling limits, and how you have in at least some idealized world, a perfect evolution from an antiferromagnetic insulator to a Fermi liquid, and this always goes by this intermediate state, which is an antiferromagnetic metal, which has electron pockets. You can now also change the density. And then you can see that once you change the density, the deviation from half filling, which we call little p, is equal to the difference in density, different involved area of the electron and hole pockets. So in that case, once your density is not exactly 1/2, in this theory, it's always a metal, because because the difference in density has to be non-zero. So one of them has to be present. You can't the Fermi surfaces cannot disappear. That's just the Luttinger theorem. And that's consistent with the fact that the equal density contours, look something like this. So if you have a slightly different density, as you keep going down this way, maybe the electron pockets will disappear completely. In fact, that's what will happen. But these will remain. And the area enclosed by that will equal to the density. And they'll be, whatever the density is, the area of these won't change once the electron pockets have disappeared. They just remain down here. You remain a metal all the way down to 0 doping. Okay. So this is for density equals 1 minus p, you go down. So that's also nice. You avoid this particular insulator is very much dependent on the existence of this density. Only at that density is the insulator allowed. This is something we understood from the strong coupling approach. And it's something we see also from the weak coupling approach by an application of the Luttinger theorem. You can't just get rid of the Fermi surfaces, they have to be there all the way down to 0 doping. All right, great. Any questions in India? All right, so the next step, no, I'm sorry, I raised the original theory. So let's go back to the original theory. So what we're going to do now is again look at this region here. We're going to stay in the metal. So we'll be somewhere here, where at least in mean field theory, we don't get any antiferromagnetism. And then we're going to ask, well, let's just keep lowering the temperature and look more carefully. is there any other instability as you look at fluctuations of phi in this region? Here we're looking at now something like this. So this is sometimes called the spin fluctuation theory of superconductivity. Spin. And the idea is, in some ways very similar to the original BCS idea. BCS idea was you have lattice fluctuations or density fluctuations, phonons in any crystal, and that can mediate an attractive interaction, which leads to superconductivity and superpair formation. In helium-3, then people understood that you could have ferromagnetic fluctuations, which then can mediate P-wave pairing, which is what's observed in helium-3. And now we just apply the same idea over here, which was done originally by Scalopino et al., and look at what do antiferromagnetic fluctuations do in a metal on the square lattice, and that will be superconductivity. So basically, we're going to replace the phonon of the BCS theory by the Paramagnon. Okay, so our Hamiltonian is going to be this, so mod K. Right, so just to remind you, we're not in the antiferromagnetic metal, we're in the metal, ordinary metal. And exactly how this fits together with the phase diagram on top, well, that's a problem people are still arguing about. That's complicated, because then you have to really account for both at the same time. And it may not be sufficient to use this approach that we're using. In fact, that's my opinion, and we'll have to look at more sophisticated methods where we also have to consider the fluctuations of the antiferromagnets more seriously, not as some static autoparameter. Okay, but with that aside, so you have some on I, coupling to that. And then I have the phi fluctuations, and I'm just going to take a very simple theory for them. Some on Q and omega by omega more squared. So the one half here, and I'll call this, well, for want of a better word, what I call it in the notes. Notes in a slightly different order, sorry. Well, maybe I'll just use my new notation and not worry about it. Well, okay, I can do my notes slightly differently. So let me just call it chi inverse. It's not exactly chi inverse, but anyway. There's some quadratic, we're going to take the complicated theory for phi fluctuations and just replace it by a Gaussian theory. We had some implicit expression for this object here in the Hubbard model that may or may not be very accurate. So what we can see from here is that there's a Gaussian theory for spin fluctuations where the expectation value of phi mod squared is equal to chi. So that's why I called it chi inverse. It's like the dynamic spin susceptibility. This can be measured in neutron scattering, which there's literally thousands of experiments on the cuprates. So you can regard this whole object here as something you can measure. It's also computed in various numerical calculations to rather high order NU and all kinds of fancy stuff. So there's a huge amount of training, and we have some understanding of what this phi looks like. So this is the theory we're going to take, where you have electrons coupled to some boson, which has some quadratic action, which is actually literally exactly what BCS did, except the phi was replaced by the phonons. So, all right, so now we're going to look at phi fluctuations, not do mean field theory in phi. In that sense, this calculation goes beyond what we did above, and look at the induced interaction on the electrons. So the induced interaction is going to be something like this. Here's the electron, and here's another electron. We're going to take a Cooper pair of electrons. So C dagger, C dagger, C, C. And then you have a phi fluctuation, which is going to be mediated, which is going to cause them to interact. They're going to exchange a phi fluctuation, just like in the BCS theory, the electrons exchange a phonon. And there'll be a sigma factor here and a sigma factor here. Right. So that's the attraction that's induced, or the interaction that's induced by the phi fluctuation in between two electrons. So the difference from the phonons is, first of all, the sigma factor. And second, this phi has chi, really. Chi has a maximum at pi, not near q equals 0. Okay. And that's really the main thing you have to keep track of. How does the fact that this propagator has a maximum at pi, and the fact that it couples to spin rather than charge, how does that change the nature of the interaction? And what you can find when you do that calculation, that interaction is attractive on the Fermi surface in the D wave channel. And the reason it's D wave and not S wave has to do with several factors. There are three factors. One is the shape of the Fermi surface. Second is the presence of these sigma factors. And third is the fact that phi of Q has a maximum at pi. Okay. So now let me follow my questions. Yes.
There's something a little odd.
Yes.
Because where phi came from was
Yeah.
a repulsive interaction among the fermions.
Correct.
But so what you're actually studying is a repulsive interaction, which nevertheless you've claimed somehow generates an attractive interaction.
Right. Exactly. So it's attractive at momentum pi, not at near momentum 0. And it's attractive between opposite spin electrons. So, so what I gave you another reason for the attractive interaction earlier, which was in the TJ model. In the TJ model, what we showed was this attraction S1 dot S2, which we derived from a repulsive interaction, could be rewritten as an attractive interaction between electrons. This was the same as minus epsilon alpha beta, C dagger I alpha, C dagger J beta, mod squared. So if you had a spin singlet pair on nearest neighbor bond, for those electrons, this was attractive because they want to form a spin singlet, and that's preferred for them. So you have two opposite spin electrons moving around, then they do have an attraction to sit next to each other and form a singlet, because this, you lower this energy. That's one way to look at it. So the thing I'm going to now describe is essentially the same mechanism, but derived in a rather different way from the weak coupling side. Yeah.
I have another counter for me issue here. The phonons that cause the attraction BCS have a massive dispersion relation.
Well, the Goldstone bosons, yeah. They do. Acoustic phonons have zero energy excitations.
And so both interactions are long-range interactions.
Yeah. I mean, here, well, is it long range?
These are Goldstone bosons of the SU2 of rotation.
Yeah.
The others were of fluctuations of the lattice.
Right, yeah.
Intuitively, the other ones are kind of more naturally separated from these. Because these are other,
Yeah.
there are other degrees of freedom. These are
Yes.
nuclei that vibrate.
Right, yeah, so
There
that's,
is here, it looks like kind of you're bootstrapping here because phi is secretly also made out of the same fermions.
yeah, absolutely, yeah. So that's why this theory is not as good as BCS, absolutely. No one's really made it quantitative even today, as far as I know, unlike BCS can be made highly quantitative for many, many superconductors. This one is a long way from that, and this is part of the reason. These are just heuristic arguments. There are two different heuristic arguments. One is the large U limit, which I just summarize here again. And the other is the small u, which is what I'm presenting. I think certainly, I would say the early days of ITC, I would say Phil Anderson certainly was of the view that the superconductor that you got from this argument was somehow different from the Scalapino type superconductor that had already been predicted. There was something fundamentally different. I don't think anybody believes that today. We have a way of connecting these to show that in any fundamental sense, there's no difference between what you get, at least in the superconducting state. Even the idea of what is different wasn't clear in those days because the idea of topology and fractionalization didn't exist. But now that we understand those ideas much better, we can say that these two limits are the same. Yeah.
Maybe to connect to the same question, but did I understand correctly that the binding happens for electrons that are at high momentum or no? Because
okay, let me just come exactly to that. Because they're only interested in bindings at electrons at zero energy on the Fermi surface. They can have any momentum you want as long as you're on the Fermi surface.
But then would it be okay to consider these as 2 degrees of freedom in the sense that you have the soft electron excitations, which are defined, and then the electrons that you maybe consider like a point particle, and hard electrons that are mediated by soft.
Yes, so I think that would be a reasonable point of view, that you have these electrons far from the Fermi surface, doubly occupied electrons and all of that. You integrate them out. This is exactly what we did to get this interaction. Here, we take the high energy electrons, integrate them out, and get some phi of Q. And then now we're looking at these soft electrons on the Fermi surface, where this came from the other electrons. The point, of course, is we don't know exactly how to make that separation in a clean way.
Can I ask a question about the BCS theory? So
yeah.
There, the phonons that are relevant are not the ones at very small momentum, right? They're at the the Fermi surface.
There's some spectral density of phonons, and the acoustic phonons don't make much of a contribution.
Okay.
Yeah, it's phonons typically at the Debye energy, near the top of the maximum energy phonons that give you the most contribution to the attraction. Yeah.
The fact that we have Goldstone bosons is not important.
Yeah, it doesn't make much of a difference. Yeah.
I just wanted to double check what you said in response to Edward's question. So you have very hardcore repulsion, on-site repulsion, but you're trying to get some intermediate range attraction. Is that?
Yeah, so as you'll see that when you go to the D-wave channel, the hardcore repulsion, you can put it back in, it just cancels out. That's another reason we're preferring D-wave. That even the weak coupling approach, if I add some repulsive interaction in the S-wave channel, which is what the hardcore repulsion is, it's in the S-wave channel, it actually doesn't destroy the superconductivity. So that's an advantage of this approach. It shows you that there's an attraction, this will give you in the D-wave channel. It also will give you, if you looked at it in the S-wave channel, that's more a strong repulsion, which was there to begin with. But you'll find that nevertheless, the D-wave instability survives.
Okay.
Because it's in a different channel.
Nuclear interaction, there is something similar. There is some hardcore repulsion, but intermediate range.
Yeah. I mean, in helium-3 also, there's a hardcore repulsion, but makes no difference to the p-wave pairing because it just cancels out in the gap equation, which is what I'm going to do now. Okay, so I take this Paramagnon mediated interaction, and I'm going to get another. I'm going to write this as an effective Hamiltonian. And here, well, let me stick to the notation of my notes because I want to get all the factors of 2 right now.
Subir, just a question about the notation for the Paramagnon. Are you using phi as a creation operator of a Paramagnon?
Phi is a real field. Oh, phi is a real field, so it has both creation and annihilation. Phi can do both. So phi is something like, it's like the displacement of a harmonic oscillator. So it's something like A plus A dagger. It can either create a paragon or annihilate a paragon. And these are the vector index is just the spin index. So you can think of it that for each momentum Q, there are 3 harmonic oscillators. And they have some energy, which is the energy of the Paramagnon. And the field phi, just like the displacement field of a harmonic oscillator, is A plus A dagger.
I see, thank you.
Very similar to what you do, for example, in black body spectrum, where the electric field is like the displacement of a harmonic oscillator. Okay. So now I'm going to add an interaction, which will be plus 1/2 sum over everything in sight. V alpha, beta, gamma, delta of Q, C dagger, K alpha, C, A plus Q, beta, C, P gamma, CP gamma, C, oh no, there's no dagger there. This V alpha, beta, gamma, delta. It depends only on the momentum transfer. So if you can just literally make up this picture here, we're just doing this exchanging boson momentum Q, and we're going to assume it's at 0 frequency. So you get some interaction. So this turns out to be basically chi of Q, then sigma alpha beta dot sigma gamma delta. Okay, and as I said, even the BCS Hamiltonian can be written this way with phonon exchange. You get a different function here without the spin dot spin factors. Okay. And in the notes, I call this J of Q, so let me just stick to that. Mess things up. Well, let me just say J is proportional to chi. So in fact, if you can see that if I had done the strong coupling approach with the 1/u expansion, you get the same interaction. And this J would be the nearest neighbor interaction, which will be proportional to cosine kx plus cosine ky, cosine qx plus cosine qy. Now we get something else that involves the spin fluctuation propagator. So you can see literally it's a very similar theory that we had earlier.
You said omega equal to 0 here?
Yes, yeah, omega equals 0, that's just an approximation. Of course, what you really should do is sum a ladder of these to solve the integral equation, and that'll give you a more sophisticated, that's called the Eliashberg equation for superconductivity in the presence of dynamic fluctuations. I'm just going to make the BCS approximation and just look at static phonons. All right, so now we just factorize as before. So once you see something like this, you go ahead and factorize. by the usual rule, but we now do it in momentum space. So you just, this is all I'm doing. C dagger, CC is going to be replaced by C dagger expectation value, CC plus complex conjugate. Okay, so you apply our usual machinery to this fourth Fermion term, and you get then a set of mean field equations. So they're now in momentum space, and they're very similar to the equations we had earlier. So let me just write it out. So delta K is what I'll call as okay, well, this is not the general form of it. I have the general form of it. Okay. Yeah, so it's just equal to this. I guess I'll just leave it this way. Yeah. No, that's fine. Okay, so that's delta K. And you have the BCS equation which determines the value of delta K. Looks something like this. So delta P is equal to 3/2 sum of K, J of P minus K. Delta K. But I do have to say that this is epsilon alpha beta. So already I've done something which is non-trivial, which is if you look at this interaction the way it's written, it looks repulsive because V is positive, but there are these sigma factors. In the BCS theory, you have a term like this with a negative sign, but without the sigma factors. And when you do this kind of pairing, you get exactly the same gap equation with a plus sign here. And in the gap equation, a plus sign here corresponds to an attractive interaction. And here, what's happened is even though I have an attraction with a plus sign here, not a minus sign here, these sigma factors combined with the spin singlet, with the opposite spins, gives me a net attraction. So that's so these sigma factors tell you that a seemingly repulsive interaction without any minus sign here gives you a, yeah. All right, so I urge you to work through that. That just involves a lot of algebra with the Pauli matrices.
I'm puzzled by the role of the SU2 that was spontaneously broken. It was broken by the expectation.
It's not broken. So everything preserves SU2 here. I'm in the ordinary metal, not in the antiferromagnetic metal.
So what is the phi that is being exchanged now?
It's the same object before it was broken.
Oh, so this is only in the phase where it's not, so it's not in the phase we discussed before.
Yeah, so as a function of U, I had phi. I had 3 phases. I had here a metal. Here I have an AF metal. And here I have an AF insulator. I'm here.
Okay, so why is phi light? Why does it mediate this interaction?
Because I'm assuming I'm close to this instability. So it's mass. So the mass of phi, if it goes to 0 here, or chi inverse, chi diverges at this point. And so that's why it's a nearly antiferromagnetic metal. So these are enhanced spin fluctuations. So you measure this quantity in neutron scattering, and you find it's large. And so you say, okay, well, let me look at the effect of this large quantity on the pairing. All right, so now we have to look at this equation. This is where the fun stuff happens. I hope I get this right. Okay. Okay. Sorry, I've kind of messed things up here a little bit. Better prepared. Okay, there's a minus sign here. Okay. Yeah, so. Yeah, there's a lot of minus signs to keep track of. I got this minus sign wrong, I believe. So J, well, here. Yeah, okay. Right, so I guess that makes sense. Once you integrate on the boson, you always get this comes in the opposite sign in here. Yeah, okay, now I'm consistent with the notes, and sorry, I forgot about that minus sign. Anyway, so there's some interplay between this and the spin singlet pairing, which gives you this equation. That's correct. Okay, so in fact, this is negative. Yeah, that's right. This J is going to be negative. You're going to have to work hard to find a solution of this. So now in the BCS case, if this J was negative, well, so what happened in the BCS case is that the sigma factors are not there, and J is indeed negative. But because the sigma factors are not there, you get an opposite sign here. And then this thing has a nice solution, because if J is negative, the net factor here is positive. And then there's a solution where delta is a constant, and this delta and that delta accommodate the same sign. But now what's happening is because of the spin dot spin factors, I'm getting a negative interaction, and this doesn't obviously have a solution. But let's see how we can find a solution. So let's take our Fermi surface. And now I'm going to center it at, so that I can draw a nice circle. I'm going to center it at pi pi. So here's our Fermi surface. Shifted all the momentum by pi pi. That doesn't do much. And so this is epsilon k equals 0. Okay. So now let me pick, I'll say something over here. Pair of electrons here, and one over there, minus k. So these electrons are going to pair, and they'll have some pairing delta k. So they're going along these electrons. So now they're going to scatter off each other. So there'll be k and minus k. So what are they going to scatter? Where are they going to scatter to? Well, we want to do a scattering of the momentum pi pi, but that's where this object is really large. So they're going to scatter to k plus capital K, because J of k is maximum there. And minus k is the same as plus k, so fine. Because J mod J of k, that's the assumption, is large. It's also negative because it's proposed to minus k of k. Okay, so what's going to happen is that these two electrons here, let me color code them. You have these electrons here, the orange electrons. So sitting here and here. So they're going to scatter by pi pi. They're going to go here and here. So they're going to be somewhere here. They're right on the Fermi surface, and there. And this is pi. This is k. So this will be delta k of k. That will be the pairing amplitude for that. And this process will continue forever. They'll go back and forth. And every time you go from here to there, you pick up a factor of j, because p minus k is k. So now you look at this equation and see, is there any reasonable solution? Well, the signs at the very least have to match on the left and right hand side. So this is negative. They'll only match if this delta at the orange point has the opposite sign from the delta at the pink point. So we require, and that's really the simple explanation for D-wave pairing. So we require, delta at the orange point minus delta at the pink point or solution of the gap equation. And that's the basic reasoning which you have to go through, and involves, first of all, knowing the shape of the Fermi surface and finding which points of the Fermi surfaces are separated by the wave vector which the susceptibility is the maximum, and looking at the strength of the interaction at that wave vector, and then so it's a complicated business, but this kind of heuristics is actually remarkably successful. And predicts, the nature of the pairing, the D wave, S wave, singlet, triplet, so on. So triplet pairing tends to go with ferromagnetism. Singlet pairing tends to go with antiferromagnetism. Not surprising. And but that's D. The D wave pairing is preferred when you can connect points in the Fermi surface by the antiferromagnetic vector. In the Nick tides, what happens is there are separate pockets, small pockets, which are connected. And so they have to have opposite signs. And this leads to, when you look at the details, something called extended S pairing. It's not quite D wave, but it's an S wave type pairing which changes sign on the different pockets. Okay.
So what is the thing that eventually condenses here in terms of the seeds?
This object here.
And in what sense is it the D wave?
Because of this fact on the Fermi surface. So this is some function of K, which is the momentum of these electrons on the Fermi surface. Okay. So as you go from here to here, it changes sign. And then you can put in some other interaction here, like the short range repulsion. You'll find that when you do this integral over K, since this thing changes sign, that short range repulsion just doesn't give you any contribution, just cancels out from the angular integral over K and the change in sign of this delta K. So that's another advantage of D-wave pairing. In fact, it's kind of, you also know this in quantum mechanics. If you have an angular momentum D-wave wave function, it vanishes at the origin in the radial direction. And so that so that means that the Hubbard U repulsion, which is practically the origin, doesn't have much of an effect.
Would all these spaces and so on exist in 3 dimensions also, or this particular?
Yeah, so in fact, the original Scalopino paper was 3 dimensions, which is before the discovery of the cuprates. Yes, I think of course, the heavy fermions, I think uranium, beryllium 13, if I may be remembering wrong, those are 3-dimensional antiferromagnet. Cerium copper 6, I think is the best example. Cerium copper 6 is a 3-dimensional cubic crystal, which has antiferromagnetism and analog of D-wave pairing. Yeah. I mean, the angular, it becomes more complicated. You have to look at representations of the space group of the crystal. You can't call them D and S. There's some more complicated names, D1G, A1G, and so on.
They're also superconducting at sufficiently low temperatures, but
yes,
they're not high DC superconductors.
Correct. Yeah, those TCs are very low, 1 Kelvin or below, right? But the heavy fermion compounds are, many of them are in a similar class, at least as far as the pairing is concerned, and the magnetism.
They also have these strange metal base.
Most of them do, yes. And that's one reason for believing that there's some more dimension-independent explanation of the strange metal. So these kind of local ADS2 or SYK type theories have, some appeal for that's one of the reasons. Yeah. Okay, great. Any questions in India? All right, so this is all in the notes, although in a slightly different order, and hopefully that could also, I don't think there are any sign errors. If you find sign errors in the notes, please let me know. And then next week we're going to start, we go back to the half-filled insulator and spend quite some time on it, and this time look for more exotic phases in the half-filled insulator, of which, you know, the whole field has developed, which didn't exist at the discovery of the time of discovery of cuprates. The field of fractionalization and emergent gauge fields, and I hesitate to use the word topology because now it seems to mean something else entirely, but topological order, which developed after the discovery of the high TC and also in conjunction with work on the fractional quantum Hall effect. I will mostly focus on the high TC type applications eventually, and maybe occasionally I'll mention the connections to fractional quantum Hall effect too. Okay, so see you next week then.
All these questions. Just
No,
I control myself.
You keep me honest and correct my
I'm
mistakes.
trying to understand every detail.
Great.
I'm exhausted after these lectures. Can't imagine.
Okay, good. Me too.
That's natural, because the speaker is always tired, but I sit here trying to absorb everything. Hello. Hey. How's the piano?
Okay.
So if main is good with it. If main is good with it.
Yeah, I don't know if she's responded, but yeah. But, yeah. Please turn this off. Well, I will do it at my office.